Inside a few rare atomic nuclei, a decay can proceed so slowly that its half-life runs far beyond the age of the universe. In the ordinary version, 2 electrons come out, and 2 neutrinos carry away part of the energy. There is another possibility. If those 2 electrons ever come out carrying almost all of the decay energy on their own, with nothing missing, the implication would be extraordinary. It would suggest that the neutrino may be its own antiparticle, and that one of physics' quiet bookkeeping rules can fail. In this video, we follow that single clue from the nucleus itself to the underground experiments waiting in the dark for a signal no one has confirmed. To see why that missing energy clue matters, start with the version physicists already know is real. It is called 2-neutrino double beta decay. In a few special nuclei, an ordinary single beta decay is blocked, or so suppressed that it almost never happens. A slower, more delicate route is still allowed. 2 neutrons in the nucleus turn into 2 protons. 2 electrons are emitted. 2 antineutrinos carry away the rest of the lepton bookkeeping. This is established physics. It is a second-order weak process which helps explain why it is so rare. The important part for experiments is simple. The decay has a fixed energy budget, but the electrons do not receive a fixed share of it. The neutrinos can carry off different amounts each time. So when researchers add up the electron energies over many events, they do not see one sharp line. They see a broad continuum. Now we can ask the harder question. What would have to be true for the same kind of nucleus to emit 2 electrons and no neutrinos at all? The standard answer is simple to say, and strange to accept. The neutrino would have to be a Majorana particle. In plain language, neutrino and antineutrino would not be fundamentally different particles. They would be 2 faces of the same thing. In the usual picture of neutrinoless double beta decay, one part of the nucleus emits what looks like an antineutrino, and another part absorbs what looks like a neutrino. That handoff works only if both labels can describe the same underlying particle. Otherwise, the process cannot close. If they can, the neutrino never appears as a free particle escaping the nucleus, and the decay energy can end up in the 2 electrons instead. That leads to the deeper reason physicists care so much about this decay. Particle physics keeps a running count called lepton number. An electron or a neutrino counts as +1. Their antiparticles count as -1. In ordinary weak processes, that ledger balances. If an electron comes out, an antineutrino often comes with it, and the total stays unchanged. But in neutrinoless double beta decay, the final state would contain 2 electrons and no balancing antineutrinos. The total would shift by 2 units. If this decay is real, lepton number is not an exact law of nature. It is a rule that usually works until a very rare process reveals the crack. That is a large conclusion to draw from one tiny event inside one nucleus. This part of the story needs some discipline. A detection would carry enormous weight, but the conclusions would not all have the same status. One result would be direct and unavoidable. Nature violates lepton number. Beyond that, the standard interpretation is that neutrinos have Majorana character, meaning a Majorana mass term exists for them. There is also a famous argument, often called the black box theorem, which says that any real observation of this decay implies Majorana mass somewhere in the underlying physics, even if the microscopic mechanism is more complicated than the simplest neutrino exchange picture. One detection would not answer everything. It would not, by itself, tell us exactly which mechanism produced the decay. It would not settle every detail of neutrino mass. And it would not, on its own, prove how the universe ended up with more matter than antimatter. It would be a breakthrough. It would not be the final word. How do you search for a decay defined by particles you never see? The method is clean. You do not need to catch the neutrinos themselves. You measure the energy carried by the 2 electrons. In ordinary double beta decay, the nucleus has a fixed amount of energy to release, and that energy is split 4 ways, 2 electrons and 2 antineutrinos. Because the neutrinos can carry off different amounts each time, the electrons do not leave with one fixed total. Their combined energy spreads across a continuum. In the neutrinoless version, no neutrinos appear in the final state to take any of that energy away. The 2 electrons carry almost all of it. So instead of a broad spread, you get one specific total energy. A narrow peak, one exact node at the endpoint. That is the search in its simplest form. You are not looking for a dramatic new particle crossing the detector. You are looking for a tiny event where no energy is missing. The theory behind it is subtle. The experimental clue is direct. Now the difficulty comes into focus. If the signal sits at one exact energy, then almost anything that deposits a similar amount of energy can fake it. That is why these experiments go underground. They go there for silence. Cosmic rays constantly strike Earth's surface, and ordinary rock, concrete, and metal carry traces of radioactivity. In daily life, that background is harmless. In this measurement, it is noise loud enough to bury the question. So teams place detectors deep below mountains or inside mines. They surround them with shielding. They build them from materials chosen for extreme purity. Sometimes the copper, cables, and bolts become part of the physics problem. Then comes the patience. The half-lives under test reach 10 to the 26 years and beyond. No one waits for one nucleus to survive that long. Instead, researchers watch an enormous number of candidate nuclei at once for years and hope for a few genuine events. This search depends on more than looking harder. Teams have to build an artificial quiet, deep under Earth, where one forbidden decay might stand out. This is where the field can start to sound like a blur of isotope numbers and experiment names. The logic underneath is simpler. Physicists use different nuclei because each one offers a different advantage. Germanium-76 can be made into detectors with exceptional energy resolution, which matters when the signal should appear as one sharp line. Xenon-136 can be deployed in large quantities in liquid or gas, which helps when rarity is the problem. Molybdenum-100 and tellurium-130 bring their own strengths in decay energy, detector design, and scalability. These are not separate stories. They are different instruments tuned to the same question. Did a nucleus emit 2 electrons and nothing else? Some detectors measure energy with extreme precision. Some reconstruct the event shape, so background looks different from signal. Some work at cryogenic temperatures, where an almost impossibly small energy deposit can still be measured. Others gain power from size by watching more nuclei at once. The details change. The logic does not. Many isotopes. Many technologies. One yes or no question asked from several directions at once. Now we reach an important complication. Even if a detector sees neutrinoless double beta decay, the raw result does not give you a neutrino mass written neatly on the screen. What the experiment measures is a decay rate, or more often a lower limit on the half-life. Theorists then connect that number to the effective Majorana mass, often written m beta beta. In the standard light neutrino picture, that quantity depends on the neutrino masses the way neutrinos mix, and extra phases that matter only if neutrinos are Majorana particles. One more ingredient sits in the middle, the nucleus itself. The decay happens inside a complicated many-body system, and nuclear structure affects how readily the process can occur. The needed calculations called nuclear matrix elements are essential. They also carry real uncertainty, so the situation has an odd split. The experimental signature can be clean. The interpretation still has some blur. A half-life can point to a neutrino mass scale, but that conversion depends on theory that is not yet settled. That is why a non-detection still matters. It pushes the allowed mass range downward. And that is why a detection would begin a richer story rather than end one. It would tell us something profound is true. Then physicists would have to work out how nature is doing it. And this is why the search widens beyond neutrino physics. If neutrinoless double beta decay is confirmed, then lepton number is not an exact rule of nature. The ledger does not always balance. That matters because the early universe ended up with more matter than antimatter. Physics still does not know how that happened. Many of the strongest ideas require the bookkeeping symmetries of particle physics to break, at least under some conditions. In that larger picture, a tiny decay inside one nucleus starts to matter on a cosmic scale. It would not prove a full story of cosmic origins by itself. It would not confirm leptogenesis on its own, or identify the exact mechanism that tipped the balance in the young universe. We have to be careful there. but it would strongly support a world in which lepton number violating physics is real, and in which the neutrino is tied to that deeper story. The remarkable part of this search is the change in scale. We begin with 2 electrons inside a buried detector, and we end with a sharper view of why a universe filled with matter may have been possible at all. That larger cosmic implication brings us back to the present, and to a simpler question. What have the experiments seen? So far, no confirmed neutrinoless double beta decay. No accepted peak at the decay energy. No result the field treats as a discovery. That may sound uneventful. In this search, silence counts as data. Each year a detector sits underground and does not see that sharp line. Researchers push the allowed half-life farther out, above 10 to the 26 years in leading programs, depending on the isotope and the analysis. Put plainly, if the decay happens, it is even rarer than many already extreme expectations. Searches like Camlanzen and the germanium efforts that led into Legend have done more than wait. Researchers have learned how to clean up the silence. Better radio purity, better background rejection, better energy resolution, less chance for an ordinary event to pass as an extraordinary one. That matters for theory. If the usual light neutrino picture is right, these null results tighten the allowed range of the effective Majorana mass. One caution matters here. Converting a half-life limit into a neutrino mass limit depends on nuclear matrix elements, which serve as the nuclear structure conversion factors for this decay. And those calculations still carry real uncertainty. So the experimental statement can be sharp while the mass interpretation stays blurred. Even so, the field is not standing still. Non-detections already shape which models still fit comfortably, how researchers talk about parts of the mass ordering landscape, and how sensitive the next generation of detectors must become. This is a narrowing corridor. That is why the whole field is listening for one specific sign. 2 electrons emerging from a nucleus with no energy missing. If that peak is confirmed, with backgrounds understood and the statistics secure, several things change at once. First, neutrinoless double beta decay is real. Second, lepton number is not an exact bookkeeping rule of nature. Third, the neutrino does not fit the ordinary Dirac picture of a particle with a separate antiparticle. In the standard reading, it has Majorana character. The logic of the subject goes further. Even if the microscopic mechanism proves more complicated than simple light neutrino exchange, observing the decay at all still implies Majorana neutrino mass at some level. A discovery would not answer everything. It would not tell us the exact mechanism inside the nucleus. It would not give us the full neutrino mass spectrum. And it would not prove that leptogenesis explains why matter survived the early universe. It would establish that nature allows the kind of lepton number violation those larger ideas require. So we end where we began. A tiny event in a rare nucleus watched for years in deep underground quiet could settle one of particle physics' simplest and strangest questions. Is the neutrino, in some fundamental sense, its own antiparticle? If the answer arrives, it may come as nothing more than 2 electrons carrying the whole energy budget by themselves. That would be enough to redraw the boundary between particle identity, broken symmetry, and the history of matter. If you want more calm deep dive science like this, you can like the video and subscribe. Thanks for watching.